We have seen the application of Schrödinger equation as particle in 1D box, the expression of energy that we obtained in particle in one-dimensional box, which is further utilized to determine the energy of transition between HOMO, that is highest occupied molecular orbital, to LUMO, that is lowest unoccupied molecular orbital in polyene molecules. Polyenes are all those molecules that contain several number of conjugated single bond and double bonds. Butadiene molecule is such an example where you can see the molecule contains more than more than one double bond, and the arrangement of double bond and single bond are in conjugation. Now we will see the highest occupied molecular orbital of butadiene. Butadiene constitutes four carbon atoms, and these four carbon atoms contain um, unhybridized p orbital, and each of these unhybridized p orbital contain one electron, which when undergo combination to form four molecular pi orbitals, then results in formation of equal number of 4 pi molecular orbitals. Out of this, half of the molecular orbital is bonding molecular orbital and other half are anti-bonding molecular orbital. So two are bonding molecular orbital, pi 1 and pi 2, pi 3 star and pi 4 star are anti-bonding molecular orbital. The electrons, the total number of pi electrons are 4, that was in butadiene molecule. In pi molecular orbitals, these 4 electrons are to be placed. The first 2 electrons are placed in the lowest possible molecular orbital energy level, that is pi 1. Since each of the molecular orbital cannot accommodate more than 2 electrons, then the rest of the electrons are filled in pi 2 molecular orbital. Since the pi 2 molecular orbital, it is the molecular orbital which is occupied and it is the highest energy level than pi 1, higher in energy in comparison to pi 1. That's why it is called highest occupied molecular orbital. And pi 3 star and pi 4 star, among these, the pi 3 star is unoccupied just like pi 4 star, but this is the energy molecular orbital which is occupying the lower energy in comparison to pi 4 star and lowest possible unoccupied molecular orbital. That's why it is called lowest unoccupied molecular orbital. So whenever these kind of molecules are allowed to interact with the external source of energy, there is a possibility of transition of electrons from pi 2, that is HOMO, to LUMO. So the amount of energy that is required for the transition of electrons, it is easily calculated with the help of energy expression of particle in 1D box. The energy expression was n square h square divided by 8ml square. Here the energy of transition is calculated between two successive energy levels. So if we consider the HOMO, it is indicated by n, then LUMO can be indicated by n plus 1 because it is the next higher energy level. So n plus 1. So after the subtraction, the formula that comes 2n plus 1 h square divided by 8ml square. Now we need to calculate length of the box, that is capital L, and n, from where the transition is occurring. It is very easy to determine. As you can see, the transition is occurring from HOMO, and HOMO is second molecular orbital, that is the second energy level. So the value of n is here 2 because from the 2 energy level, that is the second energy level, the transition is occurring. So the value of n here, it would be 2, and the value of m, since we are dealing with the electrons, so the particle is actually the electrons. That's why we can place the mass of electron in place of mass of particle, and then we will calculate the length of the box. The length of the box is actually the length of molecule. So what is the length of molecule? Length of the molecule is end-to-end distance of the butadiene molecule. End-to-end distance, I'm drawing the structure of butadiene molecule. CH2 double bond CH, single bond CH, double bond CH2. Here you can see there are 2 double bonds and 1 single bond. The single bond length is 154 picometer and double bond length is 135 picometer. So the total length is not only the end to end distance, but it is further extended by 77 picometer in right hand side and 77 picometer in left hand side. Why? Because it is believed that the molecule may get stretched all the time because of the vibrational energy, and the stretching is about half of the length of the single bond, and which is 77 picometer. So it is further extended left and right hand side, that is both sides, by 77 picometer. So the length of the box is actually the length of the molecule. We are considering the molecule is here linear, although it is not. But since we are dealing with a system where a particle should be inside a one-dimensional box, so we are here considering the molecule is linear. It is having only one dimension, that is the length, and the length of the molecule is end to end distance. So the length of the box is equal to 1 into single bond length, okay, plus 2 into, since here we are having two double bonds, so we have multiplied 2 with double bond length, plus extra 77 picometer in both sides of the molecule, that is 154 picometer, further extension for the molecule. Okay, so the total calculation, 1 into 154 picometer plus 2 into 135 picometer plus 154 picometer. So 154 picometer into 2 plus 135 picometer into 2, 308 picometer plus 270 picometer. So the total is 578 picometer. So total length of the molecule is 578 picometer. We can represent it in terms of meter, 578 into 10 to the power minus 12 meter. So this is the length of the box and this is the length of the molecule. Now the particles are actually the electrons. The electrons are delocalized in all over the molecule, and that's why the particle is flowing inside this box. Okay, so now we will calculate the energy gap by applying the formula, because we are having all the things that is required for the calculation of delta E. I'm just writing the formula to calculate the value of N. N is equal to total number of electrons. This is applied only for polyene molecules, divided by 2 is equal to total number of pi electrons. Actually these are pi electrons, so total number of pi electrons was 4 for butadiene molecule, divided by 2, so the value of N is here 2. Okay, and the mass of the particle is here the mass of the electrons, because these are the pi electrons which is delocalized in all over the butadiene molecule and can be correlated with a system like particle in one dimensional box. So the mass of the electron is here n 9.11 into 10 to the power minus 31 kg. We will use all these values to calculate the delta E value. So we have seen the formula of delta E. So delta E is actually 2n plus 1 into h square divided by 8m L square. So one by one we will put all the values. 2 into 2 in place of n, we are putting 2 plus 1 into h square, 6.626 into 10 to the power minus 34 joule second whole square, okay, divided by 8m 9.11 into 10 to the power minus 31 kg into L square. So length of the box that we had calculated, that value is 578 into 10 to the power minus 12 meter. Okay, so we will calculate the value to this 5 into 6.626 into 6.626 will give you 43.90. Okay, into 10 to the power minus 68, because there is a square, okay, joule square into second square divided by 8 into 9.11 into 578. Oh, there was a square, my mistake, square. Okay, so 578, first we will write it in 5.78 into 10 to the power minus 10 in this manner, meter whole square, and here it is meter square, and here we are having a kg because of mass of the electron. So 5 into 43.90 into 10 to the power minus 68 divided by 8 into 9.11 into square of 5.78 will give the quantity 33.40, and then 10 to the power minus 20, and there is another quantity 10 to the power minus 31 for the mass of electron that we missed here. There is a quantity 10 to the power minus 31, 9.11 10 to the power minus 31 for the mass of electron. Okay, and joule square in place of kg meter square, it was in numerator, so when we are taking it in denominator it will become by second square. We can rewrite the expression like this. Okay, so after multiplication of 5 we are getting 219.50 divided by 8 into 9.11 into 33.40. We will add up the powers of 10 minus 68 plus 20 plus 31. As we know that kg meter square per second square is actually the joule square divided by joule. Okay, so 219.50. After multiplication of these three quantities we will get 2434.192 into 10 to the power, after addition and multiplication you will get minus 17, and here joule will cancel out each other, so 1 joule will come. So 219.50 divided by 2434.192 into 10 to the minus 17. No, same expression I have written. Okay, that's fine. So after the division we will get the quantity 090173. This is the quantity 090173 into 10 to the power minus 17 joule, or we can rewrite 9.02 into 10 to the power minus 19 joule. This is the delta E value, and it was verified that the experimental values are almost similar to the values that we have calculated theoretically by applying particle in 1D box energy expression. Okay.